It is said that around 90% of the goods we use every day is imported from overseas. Ocean freight remains one of the most popular means of moving goods around the world. It has become economical and reliable enough for our post-industrial revolution society to transport millions of tons of raw materials, partially finished goods, and fully finished goods around the world every single day. For better or for worse, our globalized economy is dependent on the world's shipping routes and the ports that service them. As technology continues to evolve, so too must our shipping ports. A smart port is an automated port that uses data analytics and artificial intelligence to perform daily operations more efficiently and economically. It is said that implementing automated processes will not only benefit the port, but the wider supply chain as well, as the flow of cargo around the world is unimpeded by instances of delays or untoward incidences in and around ports. Key components of the smart port include smart infrastructure, which is utilizing space efficiently and securely, smart traffic flows, which means smooth traffic flow with no delays, and smart logistics, which is the efficient movement of goods. As the world is slowly transitioning away from 4G to 5G, development is already well underway to realize the expectations of 6G, which is projected to be up to 100 times faster than 5G when it arrives by 2030. Smart ports adopting 5G and beyond 5G technologies are expected to be safer, more efficient, and capable of handling an even greater volume of cargo compared to today. However, this transition is not without its challenges. Smart ports are expected to be outfitted with a range of Internet of Things enabled devices that must capture and transmit a tremendous amount of data for automation purposes, such as AI-assisted vessel management, inventory management, and intelligent video surveillance, among others. With regards to the OSI model, a tremendous amount of data would need to be encapsulated and decapsulated as they move from one end to the other through the physical layer. Hence, smart ports need to have the bandwidth to support these devices and the amount of data that needs to be shared between them. Moreover, according to Huawei, most ports of today usually have fixed networking infrastructure. In terms of the OSI model, these are physical connections between the sender and receiver, usually comprising of fiber optic cables. Traditionally, the upgrade or retrofitting works have always been extensive, costly, and time-consuming, not to mention disruptive to daily port operations, which also costs the port money in the form of lost revenue. Moreover, as smart ports are expected to be outfitted with a wide range of Internet of Things devices, wireless networks will be more feasible as they are more easily deployed and replaced as necessary. Next, present-day 4G network solutions present latency, bandwidth, and range issues, which still prevent them from being incorporated into automating certain processes. For example, current smart ports are able to incorporate fully autonomous cranes and straddle carriers to load, unload, and sort cargo containers. However, transporting these containers autonomously on public roads outside the port into cities remains unfeasible, as autonomous vehicles still cannot react fast enough in unexpected emergency situations. This is especially concerning as a fully laden large goods vehicle can weigh over 36,000 kilos. Ergo, the autonomous technologies in the smart ports and harbour cities of tomorrow need to be able to account for instances of human error to mitigate mistakes and safety risks. In this part, we'll be discussing some possible solutions to the challenges pointed out earlier. Basic wireless systems, which are single input, single output, or CISO, are limited in terms of power and bandwidth, and are susceptible to environmental interference from objects such as buildings and trees. Moreover, there are limited paths available between the host and client. This is not ideal, as information transmitted from a source may not be interpreted correctly by the receiver. For example, signals may reflect off surfaces, causing data packets to arrive out of order at different times. They may also be affected by unwanted noise from the environment. Additionally, in networks with limited bandwidth, congestion can occur in CISO systems, which is unacceptable in cases where low latency is prioritized. 5G Multiple Input Multiple Output, or MIMO, solves this by incorporating multiple antennas at the transmitter and receiver such that there are more paths available for the data to be transmitted. Crucially, MIMO can ensure reliability by providing a form of redundancy, as the same data can be transmitted through more than one antenna. At the receiving end, signals are recombined such that even deprecated signals can be identified and aggregated to reproduce the transmitted data. This means there's a lower chance that the data needs to be retransmitted. There are various ways to implement MIMO. In this video, we'll be discussing how beamforming and multiplexing could be implemented in beyond 5G smart harbours and surrounding cities. First, let's talk about beamforming. According to Nokia, massive MIMO or MIMO systems that incorporate a large number of antennas are able to perform beamforming, which is a technique in which systems with more than one antenna can focus wireless signals to a specific receiving device. For devices that are far away, directing signals like this allows the receiver to receive a much better signal quality, which results in much faster information transfer with fewer errors. Beamforming is especially useful in 5G networks as the frequencies operate along the millimeter wavelength, which, while faster, is much more sensitive to blockage and interference compared to 4G wavelengths. This is particularly useful in smart harbour applications, as a typical shipping port can encompass a large area with varying topology. Additionally, beamforming could be useful for land-sea communications to retrieve data from weather monitoring instruments or ships as they approach or leave harbours. However, researchers point out that the downside to this is the cost associated with installing more 5G-compatible repeating antennas to circumvent signal blockage, especially in indoor areas. However, it's expected that the cost of these installations will come down as more and more use cases for 5G and beyond 5G technologies present themselves over time. Next, we'll talk about multiplexing. Spatial multiplexing prioritizes throughput over reliability by transmitting frames over multiple unique path streams before recombining them at the receiver. The receiving device is able to identify and select the strongest signals to recombine these frames, which maximizes the amount of data that can be transmitted per unit time. For example, the sender may want to send a message, Sunway University. In multiplexing, that message may be split such that Sunway is transmitted through one antenna, while University is transmitted through a second separate antenna. The message is then recombined at the receiving end. This is particularly useful in smart ports and applications where throughput is prioritized. For example, a vast amount of data needs to be transmitted and processed for AI-assisted tasks. This can include the sensor and position data communicated between autonomous straddle carriers and cranes. It should be noted that MIMO multiplexing can be considered computationally expensive as devices must split and recombine frames, but it is projected that processing power will improve over time. To complement the system, Ericsson also proposes radio stripes. Instead of passive cables connecting one antenna to a central controller, several antennas could be installed on the wire to form a massive MIMO system, turning the wire into a part of the network architecture. The benefit of this is the scalability of the network, providing connectivity with a wide coverage area easily in a cost-effective way. In current smart harbours, it's typically located near seas where internet connectivity is poor. This would help alleviate the range issues discussed earlier and would allow for more effective MIMO beamforming and multiplexing. Lastly, let's discuss some possible network layer enhancements. In IPv4 and IPv5, a packet has been designed as an emulation of traditional postal letters, which consists of an envelope, a header, and some sheets of text, a payload. In modern postal services, such as Post Laju and J&T Express, on top of the default services they provide, users are able to customize the service based on their preference with an extra piece of paper as an instruction. For example, ensuring 3-day delivery or 24-hour delivery. The instructions express some delivery guarantee that serves as a contract between the customer and the mail carrier. The same idea can be used as a new direction in extending IP with new capabilities and services similar to how modern mail carriers enhance traditional postal formats. Within the network layer, packets could extend in a similar way by attaching a contract to the traditional IP packet. Using the contract, customers can request timely delivery or latency guarantee of tracking depending on the priority of the packet. One benefit of this in the application of smart ports is to maintain continuous connectivity and low delay for port equipment that's in the midst of providing a crucial service. The contract is a new component not found in IP packets today. It allows the inclusion of semantic metadata in the packets that can be used to establish service-level guarantees as well as novel schemes that facilitate service assurance and operations. Examples of semantic metadata include service-level objectives, directives that give guidance to treatment of packets and flows, as well as measurement and telemetry data for the packets in transit. Moreover, given the large scale of services that smart ports must accommodate, The association between a service and a fixed format address in the current mobile network system will be inflexible and difficult to provision. Hence, beyond 5G IP packets should also support both header and payload customization. The header of the network layer's packet should evolve to allow greater flexibility regarding how systems may be addressed. It should be able to accommodate a wide range of address schemes of various address structures, semantics, and lengths. The header should also aim to fix security-related aspects of existing IP address headers, such as unauthenticated source addresses, which today make them vulnerable to a wide range of attacks. Similarly, the user payload should classify the parts of a frame into objects according to their quality or importance. This allows the network to treat it in a differentiated manner. Thus, when the application data is packetized for transmission, qualitative information can be supplied through new IP contracts to give higher priority to certain IP packets on the network over others. In closing, 5G and beyond 5G enabled technologies are crucial for many automated tasks in smart ports to make them more safe, efficient, and cost-effective. As 5G and emerging 6G technologies continue to progress, it is expected that technologies such as MIMO will greatly impact our lives in the future. The speed and bandwidth afforded by beyond 5G technologies is said to be crucial for applications such as autonomous transportation, the metaverse, and precision robotics. It'll certainly be exciting to see what other applications the technology can be applied to as we approach 6G. That's it for our presentation. Do drop us a comment if you have any questions or queries about how beyond 5G technologies are crucial for building smart ports and harbour cities. Thank you.